In this video, we're going to cover the electrophilic addition of hydrogen halides to alkenes. So this is one of the most fundamental reactions in all of organic chemistry, as it shows how alkenes can behave as nucleophiles and how hydrogen halides can add across a double bond. Alkenes are rich in electrons because of their pi bond, which is their double bond. That pi bond can act as a nucleophile, and it can attack an electrophile. Our hydrogen halides, I'll just write it as HX, they're polar molecules. Since our halide is going to be much more electronegative than our hydrogen, we're going to have an electron withdrawing effect here, making our halide more negative and our hydrogen a partial positive. So in this reaction, the alkene pi bond will attack our proton, and then the halide will attach to the carbocation that it forms. This reaction is going to happen in 2 steps, and like I previously said, we are going to have a carbocation intermediate. Let's take this example that I have here of this alkene. If we come into contact or relatively close with an H bromine, like we said, there's going to be a polarity difference here. This is going to be a partial negative, this is a partial positive. The electrons from our pi bond are going to act as a nucleophile, and they are going to attack, since they are negatively charged, they're going to attack the partial positive of our H bromine molecule. This is going to break our double bond, and the hydrogen is going to bond to one of those carbons that was previously involved in that bond. But which carbon will it add to? This is called Markovnikov's rule, which basically states that when you have electrophilic addition, the electrophile, which in this case is the H bromine, will add so that the most stable carbocation forms. If we look at our electrophile and we see where we'll have the most electron density, where our carbocation, our positive charge, will be the most stable. Well, if we look at the carbon on the left side of the double bond, we have 2 alkyl groups acting as electron donors, so they're going to donate electron density. Whereas the carbon on the right only has 1 alkyl group. So even though they're both getting electron density donated, the carbocation would be more stable if it's on the carbon to the left. So once the hydrogen attaches to our electrophile, we're going to see our carbocation formation here on the left, as it's going to be more stable there. And then we'll have CH2, CH3 after that. Now we have our carbocation, and that means we also have a bromine ion. And this bromine ion, negatively charged, is going to be attracted to our carbocation. Before we see the product, if there is any type of rearrangement that can occur, this is where it would happen, right before the bromine attaches. But looking here, we have a tertiary carbocation, and we can't rearrange to get an even more stable carbocation, so there's going to be no rearrangements here. But regardless, our Br- is going to be attracted to this carbocation and attach to it, forming our carbon-bromine bond. And then the rest of the molecule stays the same. Now, one thing you want to look out for is if you see something similar to an ROOR that's involved in our reaction. This is a shortened term for a peroxide. And when we have the presence of a peroxide, our electrophilic addition is going to go anti-Markovnikov's rule. So if you think of Markovnikov's rule, where we're going to get the more stable carbocation, for the anti-Markovnikov product, we're going to have the bromine attached to the less substituted carbon. And this will be labeled in another video, but essentially with our peroxide, our mechanism is going to change to a free radical pathway rather than just the simple addition that we're doing here. If this video did help, please consider liking and subscribing, as it really helps the channel out. If you want to see more organic chemistry videos, the playlist for it should be on your screen now. Thank you for watching.